Now, how this is the link with the neutral current? This, the interpretation was this. As I said, the neutrino beam is coming from this side. This is the new mu bar beam, and we observed these signatures. And this signature was interpreted through this way: nu mu bar mediating to the Z boson, it gives nu mu bar go. And in the medium, we have electron. That electron is knocked out. This is the electron when it goes. When it go to the medium, electrons, I showed in this, I think just 1 or 2 slides back. When electron go to the medium, it produces, this is my electromagnetic showers we called. Electron gives to the photons, gamma star gives to the E plus E minus. These are the things happened here. So these are the electrons. It emits a Bremsstrahlung photon. When it emits a Bremsstrahlung photons, energy of the electron go down. So the radius of curvature of the electron is here is smaller. The photon, when it comes here, it produces the pair productions. It gives the E plus and E minus, E plus low momentum, or this is E plus. E minus, when it goes here, again emits a Bremsstrahlung photons. This photon gives to the E plus E minus. The electron is goes, and at this point electron might go out of the detector, but it emits a Bremsstrahlung photon, and that gives to the E plus E minus pair. So this is the way we try to form these pictures, even though we do not see the neutrino at all. But this is the way interpreted these pictures. And that's the most of the experimental neutrino. We try to interpret it not that. This is even more, little more extrapolated, but a little better way, but not directly to this neutrino. So again, I will say that this is okay. I tell you something which is not usually people tell, and this is the another thing I say, that this is the $1 billion pictures, $1 billion experiment, but this experiment did not get Nobel Prize. And if I say that in the last year, last century, if you give the for an experiment a Nobel Prize, my first choice will be this one. Yeah. When the pair production happen, this is the E plus E minus energy share are not always equal. In simplistic assumption, we say that if equal, to simplify these calculations, this energy can be anything of between these two. This is this electron, this is photon gives the electron and positrons. So these gamma stars, a gamma stars coming, it gives this E plus, E minus. Energy of this E plus and E minus can be anywhere 0 to almost the energy of this photon. So the energy sharing in this case, if you say that way, this is the electron, okay, one way the energy can be less. This is the electron, it carries the small energy and it carries the more energy. But in these pictures, it does not look like that. It looks like this electron is go out of the detector. Means if the detector has the final size, so this detector might go out of the detector. Okay, but other way also we may have this asymmetry of this, complete asymmetry of this my energy in the E plus and E minus. Okay, okay. Now I come back to my next thing where I stopped. So I talked about this different source, and also I talked about this is the different kind of a device where we can detect the charged particle or this eventually charged particle, the charge or electron ion, electron hole or the photons. But now I will talk about this, what are the interactions of those neutron and this detector medium, and what is the energy range we are talking, and with that energy range how we will proceed to make our detectors. So this is the beta decay. You know that the neutron go like this way, then you can say that, we say that this way, right, different way, but this is the more commonly known as the inverse beta decay. Positron plus P plus to go E plus to N. Sorry, I should, as I said that I will, I move the slide here and there too much, and this, what is the threshold? That explanation I will come later. For this, it's need this energy of the neutrino only greater than 1.86 MeV, this can produce here. Very simply, you can think about the proton mass is less than the neutron mass, about 1 MeV, and the positron mass is 0.5 MeV, and that some kinematics is required this more than this mass difference. So this is the threshold. So at this threshold, almost all reactor neutrino experiment also use the neutron captures. As I say, the neutron is produced, as I told earlier. This neutron, it will capture, it will gives you this 2 or 3 photons, that gives you this final signals to reduce the background. In earlier slides I just showed, I think somewhere. Where is the pictures? I have to go back too much. No, I don't. This is the pictures I say. This is the neutron. Depending on the material, neutron captures what is the emission of the photons. If it is the hydrogen, it gives this 1h2 and emits this 2.2. 2.2 is nothing but the binding energy of 1h2. Two separate proton and neutron, when you combine, this is the binding energy. That energy releases the photon. Similarly, in the gadolinium, if it is absorbed, it gives you the few photons of energy 8 MeV. This picture should have been there. So this is the neutrino energy. So energy release of the thermal neutron capture, as I say. So eventually the neutrino energy is that what is the energy of the positron plus this is this mass of the proton, mass of the neutron minus this. So the electron energy, positron energy, what we see, plus 1.86806 MeV. That's this, assuming the kinetic energy of the electron is neutron is 0. Okay. So this is the prompt positron energy is like this way we calculate. And here is this some kind of a neutrino interactions. We say that a proton, deuterium, or the electron, or simple atom when it happens. This is the charge current or neutral current interaction. As you say, the cross sections. Sanjay already mentioned the cross section. It is very, very small, and for this defined interaction, this is the defined kind of threshold. So if you look for the charge current interaction in the deuterium, then your threshold will be much larger. Only higher energy neutrino you can detect, but this neutral current interaction, it can happen to the 2.2. Basically, this is the neutron when it's again this produced, this deuterium is breaking up, so you have to give the binding energy that this is the energy required, that the threshold energy. So now, if you detect this neutrino, and what kind of material you use, proton or deuterium, then only you can detect the energy of the electron above this threshold only. Okay, and this neutrino energy, the neutrino reactor core, what we are using, neutrino reactor core, this is the typical neutrino energy what is produced. Neutrino core, usually we say the uranium, but in the chain there is the plutonium also produced, and this is the picture it shows. That when the neutrino started with the uranium, with time, neutron, when this fission occurs, this plutonium number is very, very more. This the uranium-238 is reduced, plutonium is increased. And this strength of this, depending on this in the reactor, how much uranium, how much plutonium, that gives you the eventually the combined neutrino spectrum. This is for the individual neutrino, individual source. What is the average neutrino spectrum? And usually when you say the uranium-235, it's the fission occurs, it is not gives only one neutrino. This whole fission chain, it gives roughly 6 neutrino. So this one of the, so this simple calculation is that in the fission roughly 200 MeV 200 MeV energy produced, and 200 MeV corresponding to give you this 6 neutrino, and that's the way we calculate what is this total number of neutrino you expect from the reactor core if you know the power. And then neutrino cross sections, as morning also I talked, the neutrino cross section increases with this energy, and this is the kind of a neutrino spectrum. It has to be go 1.8 above 1.8 MeV to cross the threshold, and then combining the product of this spectrum and the cross section, what is the observed neutrino will see, the observed neutrino will see something like this, and this is the typical pictures, and this is the, if you have this only in the different, explicitly you know that uranium-235, 238, then the spectrum will be slightly different. And You may heard recently there is a many reactor neutrino show where the spectrum difference is about 5 GeV. There is a not matching with these theoretical predictions, and still it is not clear. But most of the doubt is that in the reactor, if you vary the reactor, what is the uranium and plutonium rate ratio, then you can explain this anomaly. Okay, so this summary is that in the reactor neutrino, you have to go up the reactor energy is above this, and the spectrum is depends on this in the uranium reactor. How much is the uranium, how much the plutonium is there, depending on that, this is the spectrum will happen, and observed spectrum will also vary depending on that. And then same thing happen also in the geoneutrino also we see. Again, this is the geoneutrino, this is the, as I said, the uranium is decaying, this is the 6th neutrino, and the geoneutrino, this is the lifetime billion years. So this is in this core, we have this core, we have this uranium thorium, it comes, it neutrino produce, we can see in the detectors. But in this, one of the major source of this core nuclear is from the potassium. But if you see this energy spectrum of this potassium, this is then about 1.4, this is the end point energy. So in our present nuclear experiment, or the neutrino experiment, we cannot detect the potassium, we can only detect this is the uranium and thorium. Okay, so this is the, and this is the number of geoneutrino is proportional to the amount of uranium thorium is there. So that's the way we try to detect that in the core, how much is this radioactive material is there if you can detect this neutrino. And till now only, I will not go in detail, only 2 experiments, this Borexino and Kamland, they did this study, and they did this study and get the spectrum of this core neutrino material. Okay. So this, I say that only geoneutrino from uranium and thorium detectable right now. 40 K geoneutrino detection needs a new technology. Till now we are not doing that, anything on that. And then, of course, you know the solar neutrino. This is the neutrino spectrum. Solar neutrino, okay, I will not go to the CNO cycle, PP cycle. Basically, we say that roughly about 10 to the power 11 neutrino pass through our per centimeters area. And this is the spectrum of the solar neutrino spectrum. It shows that for the different chain, what are the neutrinos produced. PP chain, this is a cyano cycle neutrino, or in the beryllium, or this PEP, or boron neutrino, or high energy physics neutrino. This is this HEP somewhere here. Where is this? I do not see. HEP neutrino, this neutrino. So these are the maximum energy. And now I told you that some threshold for this hydrogen, helium, but there is an experiment also gadolinium, it goes to the chlorine on the interaction, it goes the gadolinium to the germanium, it interaction on the chlorine experiment, this is the Davis experiment, famous experiment, chlorine go to the argon, for that the threshold was different. And Kamiokande experiment, that I will come to later on. For that, this is for the different reason the threshold has to be roughly about the 8 GeV or so. Okay. So now again the point, when you have a detector, what kind of experiment or material you use, or other way, I say that I reverse the question. I want to use this cyano cycle neutrino or PP neutrino, then I have to use the gallium. If I use the chlorine as a target, then this gallium, this is the PP neutron, it gives this neutrino energy up to about the 600 keV. And this is this, and core chlorine, it needs that at least 800 MeV threshold energy for the chlorine. So we cannot detect this PP neutrino with the chlorine. So what kind of neutrino energy you want to detect, accordingly you have to put this what material you will use. Okay, so now this is the again this is the snow experiment where they use simultaneously, can we detect this is the charge current and neutral current. You will listen in next 2 weeks many lectures of this neutrino oscillation, how the neutrino oscillation, try to understand this, how to neutrino oscillation. This was the experiment. I will not come at all, but I am just trying to tell you. This experiment, it pin down and give the ultimate answer. So what was the strategy was that? The strategy was that we have the same instrument. In the same instrument, we will measure the charge current event and also the neutral current event. And charge current event is mainly dominated by these only electron type neutrino, and the neutral current event, this is the kind of charge current event, nu it goes to this deuterium and this proton, and neutral current interactions, this can be participate for any kind of a neutrino, any flavor independent. Okay, and the same experiment we try to measure it, and now for these two experiment, for this interaction energy threshold is 1.44 MeV. For these interactions energy threshold is 2.2 MeV, and other interaction also the charge current interaction only in the electrons, only in the nuclear. This is the this is this NNP deuterium NNP, but here the interaction happen on the electric scattering only of the electron, and this electron interaction cross section is much larger than this. The nu x can participate only in the neutral current. So this is the electric scattering rate is proportional to mainly to these electrons, and then the nu mu and nu tau, the small fractions. So I will not go in detail. Only thing I say that using these options, we can simultaneously detect this is the what is the fraction of the charge current, what is the fraction of the neutral current event. Neutral current event tells you the total neutrino flux, and the charge current interaction only give in the nu flux. And that's actually 2002. This is the pin down, that is the sun. What is the neutrino? You see that number is less, because all other cases we try to measure only this electron type neutrino, and the electron type neutrino certainly that number is less. And what other experiment predicted, this prediction was also for this charge current event are nearly the same. Okay, this is the kind of in pictures. Okay, the same thing what I showed here. This is the pictorial. It is like this. N and P go the electron, and this is the proton, and here is the neutron, and neutron gives you this again. This neutron gives you this after interaction. Neutron gives you these photons, and this is the elastic scattering. Just knock out an electron only one ring. So depending on the signatures, you can identify what kind of interaction it is. And in the morning, it was talked that in the next generation of this neutrino experiment, that the neutrino beam, or the second generation of the neutrino beam, he was showing you the things, but this is the kind of qualitatively, you say the picture was this. This is this Brookhaven lab. This beam line is going on this proton beam. Proton beam targeted hit on this beryllium target, and where this is the many particles are produced. And most of the abundant particles are this pion, and when pion comes here, pion decays to the muon and neutrino, and muon and neutrino, and then here is the large shielding block was put, where all the particle, when it go to the charged particle pion and pion k on muon, all of them will observe. And in this case, by that time people know the pion decay, pion, muon and neutrino, this neutrino flavor. This when it comes here, there is a kind of spark chamber that they try to identify this the neutrino, if it interact, it produces the electron or muon. That is the way when it comes, this spark chamber, this is the chamber is something like this is simple parallel plates. With that, they try to measure is the electron type or muon type, and then in this measurement they found that this is the all the interaction what is coming, it is coming mainly from this, it is produced this again muon. So this is what is the pion decay, this is the muon, this is the different than this, what is this muon decay to the muon and to neutrino, or this our nuclear reactions, what it happened the neutrino, that's we call that, now we call this the electron type, that time they used to call the second types of neutrino. Okay, so that's the way, and now this is the neutrino beam, and with the neutrino beam we can control many different experiment, we control the beam, and this is, I think you will have these better pictures. This is simple concept, and actually this is the concept is in the interaction particle is formed, means here what I am saying, this is the particle is coming and many charged particles are produced, and these are the many charged particles are produced. These charged particles pass through in the kind of a solid, okay, this is not the solenoidal, you can say the toroidal kind of magnetic field, where the magnetic field line with the center is going like this way. And the magnetic field line going this way or inward, now you just use the Lorentz force that tells that depending on the magnetic field within the beam pipe, either it will direct it forward only positive charge particle or negative charge particle. That's the way you can say that positive pion or negative pion. With the positive pion, that is the pi plus to mu plus and nu mu, or the negative, that is this mu minus and nu mu bar. So that's the way, and also using this magnet, you can decide that what kind of momentum range you want to choose, and this momentum range accordingly this pion decay, the two body decay, you know that, then the neutrino energy also you can restrict it that some kind of neutrino energy. And this, even though it's the mainly for this nu mu beam, but there is some secondary contamination is there. This is mainly coming from the K plus E3 decay. Basically, this is the K1 decay to the pi 0 electron in the beam. Some fraction of the pion will be K1 will be there, and that the contaminations. And this is one example of this. If you want to nu mu beam, there is roughly about few percentage of this nu E or nu E bar, nu mu bar. That contamination will be there. Okay. And okay, why I do not know this is blocked. Actually, this is the original picture is like this. Beam is coming, many particles are producing, and in these directions, only in the certain energy of the muon or pion or kaon will come, and they will decay in the long beam pipe, and at the end, all of the charge particles will stop, and here only you will have a neutrino. So this is the neutrino beam. I think you have a dedicated lecture on the neutrino beam. I will not talk much. Only thing is that, yeah, this next week you will have a lectures, and only thing is that you might not know this design, neutrino beam, this magnet is also designed by the van der Meer, who got the Nobel Prize for the WNZ discovery. He is an engineer, but he has an all this mind and do the things. And then you know, in the morning it was talked that what is the neutrino energy when pion decay in these motions, depending on the angle, energy of the neutrino will choose. So now, in this you know that T2K, when the beam was designed, this beam was designed with not the directly to this beam go to this T2K, it has within some angle about 2.5 degrees. And this design was made, and that time actually this H2K also, people knew that H2K will come, H2K position will be slightly different position than this. Now this is our super Kanye. So the beam line was designed such a way that if this beam is axis, if the 0 degree axis is in the forward directions, the beam is, pion is, proton is coming, hitting, and if this go beam in these directions, then this is the beam energy spread. Neutrino energy will be like this. If beam goes to the 2 degree or 5 degree angle, I just take only certain angle, then the beam energy will be like this, little lower and little narrower. And now you may ask why you choose this off-axis beam. By that time, you know that atmospheric neutrino, you know the sin square 2 theta t delta m23, you know that which energy, nu mu if you produce, it has a maximum oscillations. And at that energy, the nu mu bar have a maximum oscillation. For L by E, you have to take care of this, that distance, it is about 290 kilometers. Then at that which energy, distance is fixed, at which energy oscillates the maximum. So they choose this angle such that where this beam energy, most of the beam energy that, and there they can look for the maximum change in mu to nu E beam. And actually this beam was that time itself, this beam line was designed such a way that this 2.5 degree with this beam line you can have that many angle you can put. But this was put such a way that this 2.5 degree it will be valid also for the Hyperkande experiment. Hyperkande experiment also will have the same, it is may not be exactly 2.5, it may be 2.45, but it is the same angle in Hyperkande experiment also, beam will go at this angle. Okay. And then cosmic ray neutrino, this was my bread and butter last 20 years. Basically the neutrino is coming, and the cosmic ray neutrino, you have a mainly this nu mu bar, this ratio is roughly 2, and with the increase of the energy, this ratio is increasing. It's mainly because of this. With the ratio is increasing, this is the kaon ratio, kaon rate is increases, and that's why giving you this more flux. Okay, this is also another question I'll just throw to you people. In kaon, why this more kaon gives you this ratio more than 2, gradually with this energy, this number is increases. Just think about and give me the answer later. Okay, and this is this neutrino energies go exponentially fall more or less, and this neutrino energy again, these are the flux where the cosmic ray neutrino fall in the Earth's surface because the Earth magnetic field, this cosmic ray entering in the Earth's surface, the threshold is different, and because of that reason, in the different place in the atmosphere, in the Earth's surface, neutrino flux are slightly different. So this was the oscillates, for example, this is this neutrino flux, what we measured in the South Pole, what it is, what is Kamioka, and what is the ionocyte. Actually, these plots, most of the plots what you see here, it was made by this those Dighe and this KK guys, your collaborators. Holda and you people did this, all this calculation, all this. Okay. So if you ask more question, ask him. He knows all these details of this. Okay. So this was the neutrino source. Now come to a little more on this realistically in experiment. I told you threshold. So very simply, how do you calculate the threshold? Let's say neutrino coming, it come in the target, and simply say the center of mass frame. Initially, this is the neutrino energy, 4 vectors. So as I say that E plus only x-axis is this particle momentum. Neutrino mass is 0. So edu 0 0 edu 4 vectors. Target is only has the mass. No 4 vectors are 3 momentum at the 0. Now when interaction happen in the center of mass frame, you can calculate what is this. And then it produce something, it produce let's say neutral kind a lepton plus target is changing, target go to the T prime. So this our energy should be, center of mass energy should be that ml plus mt prime square. If I use this, that's the minimum energy required, then E threshold is come like this equation. Just simply this equation, if you just write it, this is the E threshold is this. Now charge current interaction in the atomic nucleus, basically this atomic nucleus, atomic electrons, basically nu E is produced, target prime, that is roughly target prime is 0. If you put this, then for this E nu, it's supposed to come n lepton by me minus 1 me by 2. That this expression if you put. Now for this nu E, this is the threshold is 0, but if it's the nu mu, then you need this kind of interaction, you need this 11 GeV energy. And for the nu tau, this needs roughly 3 TeV energy to have this interaction, for the nu tau. Okay. Now if the charge current in the free nucleus, so there are the neutron or protons, there if you put these things, again this for electron, this number is 0, E mu it is roughly 110 MeV, E tau it is the 3.4 GeV, and nu E bar, then it is this threshold, I say 1.806, earlier I mentioned many times 1.806, that the threshold, and E nu bar 130 MeV, and E nu tar is the 3.463. Now if this is the threshold, you see, this electron neutrino from sun or the neutrino reactors, this is roughly an 1 MeV. Electron neutrino, sun, this is roughly an 1 MeV, who is oscillating the mu1 and tau. So these neutrino reactors, we say that this energy of MeV, mu1 and tau, if the nu mu or nu tau, if it is happen, then your threshold has to be much larger. Okay, so this nu E oscillator nu mu or nu tau, which is produced in the sun or nuclear reactors. If you go to the nu mu or nu tau, then the interaction where you produce, this is the electron, this is a few MeV, but there you need this few MeV energy if you convert it to the nu mu tar, so cannot interact via charge current interactions, they effectively disappear. So that's what the initially happened. Similarly, atmospheric neutrino is 1 GeV, who is oscillating the tau neutrino, cannot interact via charge current interactions, and it is actually the disappear because this threshold is for nu tau, it is much larger. Okay. So that's why the initially we say that very first experiment when I say that electron deficiency, we say we did not look for this electron converted to the muon and we see nu tau, nu mu, nu tau that we see. Similarly, atmospheric neutrino also first we say that muon type neutrino is not seen, so deficiency of the muon type neutrino, and that was, we did not know that time, now I know that it transformed to the nu tau and we did not see it. And little more mathematics, all these details you will have in the next 2 lectures, but for my purpose of the experimental design purpose, these are the few mathematical expression you need. You need the oscillation. Oscillation is the sin square theta delta m L by E, that parameters you know, this is the phase what we are writing. Phase we write delta m square L by E, and when this phase is pi, that is the one oscillations happen. And now, if the oscillation is 2.3 kilo, for solar neutrino, if the energy is 1 MeV, lambda oscillation is roughly 33 kilometers for solar or reactor neutrino. But for this short baseline experiment, delta 301 is important and lambda oscillation is roughly 8 kilometers. If we just put this delta m and this delta m and L. So that's why this is this Reno, double choose those experiment to look for this sin square theta 13, they have the detectors roughly kilometers away. Now look for the atmospheric neutrino where energy is this 1 GeV, lambda oscillation it is, if you just root, it is roughly 100 kilometer for this mu to the tau neutrino. So this is this when it go to the earth surface, earth, then this is the nu mu to go to the nu tau, this is the oscillations. But for mu to E, let for example, then if you calculate or E to mu oscillation parameters, if you put these numbers, it comes, this is the roughly 33,000 kilometers, much more than the diameter of the earth. So that means oscillations in this neutrino oscillation directly, okay, matter effect will not, I did not talk about it, that's the different issue. This oscillation, electron and muon and electron, their oscillation is negligible. Only muon can oscillate in the tau, or tau may oscillate in the mu, but atmosphere only the muon type and electron type are produced. So we only talk about the oscillation of the muon type or electron type. So that's the, okay, again I am repeating, for this delta m13, why we need this 1 kilometers? Because the oscillation parameter phase is why it go to the pi, that's we go to the roughly 1 kilometers. And the atmospheric neutrino, why we only see the mu to tau oscillation, not the mu to E or E to mu? Because the U to mu, this oscillation length is so large that within that distance it does not almost oscillate. Basically the point is, if I say that this is my oscillation cycle, for mu to E, maybe it is the only these regions. Okay, we do not see any deep, but for this mu to tau, we may see the maximum oscillation somewhere here. Okay, after talking this, this is the detectors. We say that what is the some kind of detectors I was planning to talk. Let's see the planning. This I will mainly talk about the reactor neutrino, one of the reactor neutrino where the energy range is less than 5 eV, and there is a many different kind of neutrino, liquid scintillators, Kamlen, Diabe, Juno, where is the neutrino energy is the prompt energy plus this energy. And this requires the large radioactive background, means we need to tackle up this radioactive background. Dominant reaction is this, prompt positron annihilation and delay signals, that is the things, delayed signals that gives you the signals, and electron produced by the photon excited scintillator which produce the light or Cherenkov light, that is the principle we use. Other kind of experiment, the solar neutrino experiment, this is the water Cherenkov, for example, super Kamiokande, where the direct Cherenkov light from the electron produced like this, this is this electron scattering, this is the from this material, the electron will go, that electron gives you the signal, and because of the background from the neutral electron limited, this is the energy of the neutrino should be greater than this, other background is very large. And because of the oxygen is the double magic nucleus, we do not get this nu mu n to E, even though energy is more. So this nu mu n, you get this in the free electron neutron, you may get it, but here this oxygen, if you have to go the other material, that this reaction is not happening in neutrino. So in the solar neutrino, only this Kamiokande experiment, only you have these interactions, the elastic scattering interactions. And there are many other scintillator detectors for this study, Borexino, SNO, I already talked, a radiochemical Homestake says Galaxy mini experiment, and this is this gallium experiment or chlorine experiment. And then other kind of neutrino, atmospheric beam neutrino, where are the mainly this kind of beam, where the beam energy about the few GeV, and these may be the water Cherenkov detectors, Kamiokande, KM3 net, ice cube, and iron calorimeter, what are the example, or like that earlier also MINOS, ICAL, CDS, CDSS, these are the different experiment. CDSS is this experiment in 1980s at CERN, initially in the beam experiment. And liquid argon detector, Icarus, Microbune, Dune, these are the different experiment. So these are the categorized this way. And in my time, till I am planning that I will try to go through the little bit on the Juno experiment. This will take care of the most of the things. Water Cherenkov detectors, this will take only not for this Cherenkov detectors, but as I told you, this is starting from the 1980s, the detector is going on, Kamiokande to super Kamiokande to hyper Kamiokande, it has a many history. I will go through that little more time. Actually, this is coincide something, maybe I will take it till here, and Kajita sir maybe tell you the same thing after few minutes, okay, in his lectures. This super Kamiokande, that I will talk little more time, and I will talk about the Dune detectors. Basically, this is the new kind of detectors where with the liquid argon, though it started with the Icarus experiment in 1990s. And I will not talk at all anything. Okay, this is also, I will just one of the sideway will go. Radiochemical Homestake says experiment. You know this Davis chlorine experiment. David chlorine experiment in 1960s onward, 1990s, almost roughly 30 years. Every conferences he said that I see the less number of event, and but other Beckel and other the calculations say that your number is wrong or like that. Okay, but do you think that it can go 30 years that one experience said I am right and other people are going on that and nobody just interfere much? It's just going like that way. Davis was prompt on his footing. He put his foot stand that this is my experiment is right. But this, do you know this main thing what happened? There's no physicist, particle physicist, even that time did not believe this is experiment. You are saying that this is the chemical, what chemical reaction he does, we are not talking about that chemical. We are talking about the detector, charge particle going, how do you clean this chlorine to the argon, and argon is purified, you find out and one argon, this is the radiochemical test, what he do. Truly speaking, not any particle physicist did not believe his result at that time. And that's the one of the main reasons that episode went on that long time. And this is kind of, you can say that this is his chemistry, he does the chemistry. This is not the part of the physics. What he do in this chemistry, let it go this chemistry. Our physics we are doing with these other detectors. Okay, so why I told all this story? Truly speaking, still now, I try to go through his paper many times. Still now, if you tell me, I know little bit, but if you ask me to explain his experiment, how you chlorine to neutrino is a 37 argon it produces, how we count this argon, I cannot explain you. It is really a different ball game. This chemical engineering, it is different ball game. It is not our experience or our work can do that. Okay, so that's why I say that I will not talk anything on this. Okay, now let's come to this. At the morning it was talked, I just told little more on this. First neutrino detectors, when you detect, this was the plan, it was told that. But I was to tell you this physics point, detector point of view. This detector was supposed to make up 1 millimeter cube of liquid scintillators. And with this only 8 photomultiplier of 2-inch photomultiplier, and that the detector is supposed to fall here, as he mentioned, feather or foam, it will go, and the nuclear burst is happen, that time it will float, in the neutrino will interact, and that neutrino interaction that we'll see later. That was the plan. This is just after the Second World War. And then they changed the plan. So that the initial plan was, they will make, and this is the detectors, they made the detectors. This is the detectors was 90 of this, instead of 290 of this. And this advantage of the detector is the nuclear bomb, it is experimental one-time experiment. One side is something is failed, then fail. But the nuclear reactor, you have a steady neutrino. So you have a long time you can run this experiment. So this detector was made, and this concept is that same concept. Neutron and neutrino, antineutrino, positron, neutron and positron. Positron gives the 2 gamma, and neutron it captures and gives you this many gamma. That was 2 signals they are supposed to see. But these detectors was taken in the Hanford reactors in 1953. But in that area, when they look for put this experiment get something, but it has too much noise. So they could not do anything more with this design and at that reactors. And why I showed you these things, and typically people show that this is the pictures of this Neutrino Nobel Prize discovery experiment, but this is not that one. The neutrino, which Davis that the discovery neutrino, this is the experiment. They changed this design. Here they put this 1 and 2 and 3. They say that this is again go to the different reactors, and there now they put the 12-meter overburden. This is in the top on the detector top. They put the 12 meters concrete shield that reduce this muon flux comparatively much larger than this what was done in for the Hanford lab. So in this case, this is the scintillators where the neutrino will interact and produce this positron and neutron. Positron will immediately gives you this annihilation signal, and neutron will go through in between these two. They put the 200 liters of water and cadmium chloride. That's basically cadmium. And the neutron, when it comes to the cadmium and it absorbs in the cadmium and then gives you these delayed signals. And this is the kind of one of the signals. In this first scintillators, they see the oscilloscope signal. So this is the signal. That time they took the signal this way in the oscilloscope. These detectors was put and see the signals. And this was put in the another oscilloscope, and afterwards that is the delayed signal of the scintillator they have seen. So that's the way they established, and then this give the Nobel Prize. As I said, that this was the 1995, and the Nobel Prize was given. This experiment was given in 55. Nobel Prize was given in 99. By that time, this cone was not anymore. Okay, only the Rhine got the Nobel Prize along with the Davis. Okay, another thing. Okay, this is not part of the school, but I have to tell one more thing. How many of you know the Rhine? This is the guy who got this Nobel Prize, and this is the person who did this experiment in the South Africa for this, looking for the atmospheric neutrino. And now it looks like impossible or possible, you can think. So that time, who was his competitors? This was the Indian experiment, Kolar Goldfield, not very far away from here. This was the Kolar Goldfield experiment, again that was led by the TIFR. They were the competitor with the Rhine for this neutrino, for this atmospheric neutrino experiment. And of course, you know that KGF won. So that's the only thing I say, that in our institute, somebody did the experiment with the competition of the Nobel Prize winner, and we could beat the Rhine. Okay, that's the history. So now, this was supposed to my lecture in the morning. Okay, let's see how it goes. Now I talk to a little bit of Kamiokande. So I call the detector of Nobel Prizes. The Kamiokande, Koshiba got the Nobel Prize in 2002. It was mentioned for pioneering contribution to the astroparticle physics, in particular the detection of the cosmic neutrinos. And Kajita, who received the Nobel Prize in 2015, you will listen him after 15 minutes for the discovery of the neutrino oscillation, which show the neutrino have a mass. And now Hyper Kamiokande, something will happen. We expect that another Nobel Prize will come from the Hyper Kamiokande. So that's why with that context, I will say that these are the two Koshiba with this Potable TIFR, and Kajita in 1999, I think he gave this conference talks on this neutrino oscillation in the atmosphere. So now let's go back to a little bit underground. I told you that we need to go to the underground. Why we need to go to underground? That this neutrino flux is going down. Okay, I will not go in detail. Here is these things we used to put that. This was the EPR mine, South Africa, where the Ryan did the experiment. That was the deepest mine till now where the experiment happened. Then this was the KGF mine where KGF were Kolar Goldfield, and the Kolar Goldfield atmospheric neutron discovery was certainly somewhere 7.5 kilometer water equivalent depth. And as you go down, the neutrino flux is gradually going down, order of magnitude. Roughly, simple thumb rule, we say that what is the number of neutrino you see in the surface, muon in the surface, when you go roughly 1.4 kilometer, it will suppress by the factor order of 6. So that's the way the neutrino flux is going down. And Kamioka Observatory, this is what we call the observatory. It is not only one experiment. On the mountain, there are many different experiments. So this is the Super Kamiokande, and this is the Kamland experiment was there. And before the Kamland, this was the site where this Kamioka experiment was started. First Kamiokande experiment that was in this hall, it was the Kamiokande experiment was done. And also there are the many other labs who are there. There is, I think, one of the lab for this gravitational wave also there. Many other experiment was there in that underground facility. These are the connection of the different tunnels and this main road where we access. So now, Kamiokande experiment, it was not for this neutrino. In 1980s, at the beginning of the Kamiokande experiment, the main purpose was examine the grand unified theories. That time there is a theory, still it is there, but in some rule, okay, mathematically again I am saying that I am not confident to talk much. Only thing is that mathematically say that now we know that quark is the 3 quark 3 flavor, electron and neutrino could be another doublet. One of the grand unified theories, this many theories basically combine, this is the strong electromagnetic and weak interaction in one framework. Our standard model, we combine the electromagnetic and the weak interaction, electroweak. But this somehow this is the strong interaction is keep aside. But the grand unified theory all combined together. So in this theory combined together, so it has an, let's present one of this model, SU5 model, it is a 24 generator, 12 new gas bosons. So this when there is a 12 new gas bosons, you may have the many things. 7 proton can decay to the positron plus pi 0, k1 plus neutrino, mu1 plus neutrino. So this model, lepton number, neither lepton number nor baryon number was conserved. It may be violated. So and that time, this was the one of the main theoretical motivation to the many experiment. As I said, the KGF was also went to the later on much deeper. And the last KGF experiment was also for this. This is the grand unified theory, the search for this grand unified theory. Grand unified theory, one of the major signature was that proton will decay. So you look for the proton signature decay. Here the positron and pi 0. So then it will see the positron, pi 0 decay to the 2 photon, that signature you will see. That is the way, this was the motivation of this Kamiokande experiment. So for that Kamiokande, this motivation, so by that time, IMB already, this is another experiment at this USA, already they are set up, but this experiment was made. This is the detector's spherical shape, cylindrical shape. So the why we go for the cylindrical shape or spherical shape, most of the neutrino experiment, if you see, all of them cylindrical, our spherical shape. Spherical shape means here, this is the point. Nominal size of the reactor R, volume in this proportional to the R cube, but number of photosensor in the wall is proportional to the R square. On the surface we put the photosensors. So if you put circular way, then you need this from same volume, you need the less number of photosensors. And this detectors was made, and that time the first, as I told you in the morning, the 20-inch diameter photomultiplier was made. This was the Koshiba was convinced to this Hamamatsu to make this, and this detector was made, and this detectors was 16 meters high diameter, 16-meter height, and roughly 100 meters below the mountain. And this was the size is 3,000 ton, but this fiducial volume is only 1,000 ton. As I told you that in the morning, I told you this is the surface area. Usually we say that there may be lots of noise coming from the background. So fiducial volume is very small and viewed by this PMT. This was the experiment, and this was supposed to see the signature like this. Again, proton plus these signatures, you will supposed to see this kind of signatures. But these experiments what they did, that time people know the atmospheric neutrino is coming. Atmospheric neutrino was their background. This was not their signals. They studied the atmospheric neutrino to suppress what are the background they expect to see this kind of signals. So that was the starting of this atmospheric neutrino in the Kamiokande as a background, and when they look for these signals, signals try to look for the signals in the standard. When it decaying to the three particles, this all sum of these energies should be equal to the mass of the proton or neutron, and the conservation of energy, momentum conservation is the sum of them will be 0 in 2D plane. If you see what is the signal in background, they did not find, and they put the many limit of this many of this possible decay modes at that time, which is allowed by the gut. So this was happening, and that time people were thinking that we are not getting any signals from the gut theories. So, but can we go to these detectors for something else? We made the detectors, but this grand universe theory, it is not there, we do not see a signal. Can we go something else? So that time their plan was, that time they say that they have a detectors. The detectors, this Cherenkov, in the Cherenkov water Cherenkov, only about 8 boron neutrino whose nominal energy is roughly 8 MeV can be detected. These neutrino, what is the electron will produce? Electron there, the Cherenkov threshold wise does not allow that these electrons, these neutrino gives you these possible signals. So again, this is the elastic scattering between the neutrino and orbital electron is employed, and this is the way you will see. And again I said that interaction of the hydrogen and oxygen nuclei do not occur because the energy of the too low, and as I said the oxygen number is 16, that's another issue. So this is the kind of a signature they are supposed to see the sun, the neutrino is coming, it produces the electron, but only they can see these boron neutrinos, only these neutrino. HEP neutrino fraction is very small. This was their thinking. So I said that they have a detector, so that's how something can be done or not. So it was impossible to use the existing Kamiokande, that the initial detector is called the Kamiokande 1 for the study, and required the extensive work to achieve this goal. I want to go to this one of those things, but when the Kajita-san's lectures? So should I stop or I can go few more minutes? 5 minutes, okay. Okay, 25. So now these are the things as an experimental point of view you have to look. So Kamiokande 1, the trigger threshold were 110 photoelectron. Okay, photoelectron, if you come down, it is equivalent to 30 MeV energy of the 30 energy of this electron. Okay, but for this boron 80, we have to see this energy of this 8 MeV or less. So this was the threshold. Actually, Kamiokande experiment when it started, initial threshold was about 100 MeV. And that was sufficient for this my proton to nu k or mu du decay, because this proton decay to the mu nu, muon momentum is roughly 400 in rest frame, muon momentum is half of this roughly 500 MeV, so this was sufficient. But the solar neutrino, the trigger threshold of the detector should be reduced to the 8 MeV, and so then this Kamiokande 2, this was reduced. I will come to one by one how all this system was done. This was one of the electronic challenge. In addition to trigger, the background event, the low energy range should be reduced. So this, when this energy is low, background is this order of magnitude larger, so you have to reduce the background. So this is from the fall 1984 to 1986, many detector upgrade observed for this. It was mainly removal of radioactive water source, construction of the anti-counter, installation of the new electronics, and these detectors was made. So let's say one by one what it is. In this water, we have always, in the air, we have always some radon, and that always gives a background. The background is too high. So the most serious background was beta decay produced the uranium to radium series, and the nominal energy is the several MeV. Fresh water in the mine contain large concentration of radon. Supply the fresh water was stopped and closed circulation was made to employ it, and radon-free water generated system was installed. So this was this fresh water. Gradually, this is the fresh water. When we say the recycle, this concentration is reduced here. This rate is reduced. In water circulation, the uranium resin, actually this is the kind of a material which absorb the uranium from the waters, and ion exchangers, here this is the charged particle, it will exchange with this, when it go to the charged particle ion, it converted the one ion to the another ion, that was implemented. And then also prevent the contact of the water in the radon-free air mine, airtight sealing on the top of the tank were made, and the other component of the water circulation system also made in airtight. So this basically we do not allow anywhere in the cavern, there the radon is much larger. So when it was done gradually, this with this time 86 gradually, this is the my background rate is coming down the few order of magnitude. Here if it is 1, it comes to roughly 10 to the minus 4. So the background rate we could reduce that much. Also, this is the first time when the Kamikaze detector was made, there was no shield, this shielding was not there, or this is the anti-counter shielding surround the detector was constructed, this was, and this was also again a water chain of detectors. Now all the detectors has the anti-counter shielding. Basically, if any particle come from the outside, here you will see signal that will give the veto. So that was made, and main purpose of these anti-counter layers to identify the entering and exiting charged particles such as cosmic ray muon, and this anti-counter also absorb this small radioactivity in this material in the side walls. So this was also made, and then this is the PMT. Now electronics was changed. When the electronics was changed, charge and timing into the PMT are digitized PMT by PMT. So this was completely changed, and then gradually what was the Kamiokande one, this was the trigger threshold. If you put the trigger threshold, what is the efficiency of the electron? That trigger efficiencies come down to this roughly that 7.6 energy threshold, where the boron neutrino gives the efficiency roughly 50%. So all these steps were done during that, and then it come down to this my trigger rate in the electronics. Again I say the fresh water, and the other way, this gradually the trigger rate is reduced, and then this is the way when we put this air tightening this buffer. Initially when you put this fresh water, the fresh water has the little bit of contaminations, and then in this filling in this resin and this other ion exchanger it reduced, and eventually finally they come down to this almost all other background other than the cosmic ray background, and this was in the July end of this 1987. And finally trigger rate of the low energy event were reduced by more than a 3 order of magnitude, and then now we can see this solar neutrino. So I will stop here, then I will try to start from this the next day, and maybe I will skip some of the slides which today Kajita-san will show. Okay.